talk about solving exponential equations and logarithmic equations. Now that we know the properties of logarithms, we're able to solve them more easily. Let's first talk about base exponent property. As long as our base is greater than 0 and we have both bases that are equal to each other, however their powers are different, that tells me interchangeably that the powers are equivalent or the exponents are equivalent to each other. Here it says solve 2 to the power of 3x minus 7 is 32. I can rewrite 32 using a base of 2, so a base of 2 to the power of 5. And now that my bases are the same, I can set my exponents equivalent to each other, such that 3x minus 7 is equal to 5. When I add 7 to both sides, I have 3x is equal to 12. And when I divide by 3, x is equal to 4. We want to always double check to make sure this works. So when I substitute 4 into my equation, I'll have 2 to the power of 3 times 4, which is 12, and 12 minus 7 is 5. And certainly 2 to the 5th power is 32. So our solution is 4 itself. We also can use the intersect method. So using Desmos here, I've set up two equations. The first side I set equal to the left-hand side of our equation, and then I set my second line equal to the right-hand side. Using where they intersect each other will be our solution. So my blue line here is y equals 32, and my red line here is our logarithmic function, or exponential equation, of y is 2 to the power of 3x minus 7. And where they collide with each other, our x value, since we're solving for x, is 4. Similarly, if we have logarithmic functions, as long as we have log with the same base, our m and n will be equal to each other. And we can use our properties of logarithmic equalities that we learned in the last lesson when it just simply isn't possible to write each side to the equation up to a power. So it's not always going to be convenient to write both sides to the same power. So we have to use our logarithmic equalities and our properties in order to rewrite them. So let's look at 3 to the power of x is equal to 20. I can write both of these to the power, or to a log. So log of 3 to the power of x and log of 20. By multiplying both sides by the same thing, we're keeping it equivalent. I then can use my power rule to rewrite with my x out front. I can divide both sides by log of 3. And when I do that, I'll have log of 20 divided by log of 3. So x is approximately 2.7268. And when we check, if I take 3 to that power, we get approximately 20. Since our x value is rounded, our checking solution will be about rounded. So the solution is currently about 2.727 when rounded to the 3 decimal places. We also can use the intersect method. Notice that I have y is equal to 3 to the power of x as my green line, and y is equal to 20 as my orange line. And I see that where they intersect is at about 2.727. So a great way to double check that how we are finding items algebraically certainly matches what we see graphically. Here I have 100 times base e to the power of 0.08t is equal to 2500. The first thing I'm going to do is divide both sides by 100, simplify a little bit, so that I have e to the power of 0.08t to 25. I know that when I take the natural log, will get rid of my e value. Since these end up canceling each other, when I multiply both sides by the natural log, I'll have 0.08t equal to the natural log of 25. I then can get t by itself by dividing both sides by 0.08. So I have the natural log of 25 divided by 0.08 for a t value of approximately 40.2. We can double check and we'll see that it is about 40.2. And when I use the intersect method, on the left I have, or my green line is the 100e to 0.08 t, and my orange line is y is equal to 2500. And I see that where they intersect is certainly about 40.2. Here we have 4 to the power of x plus 3 is equal to 3 to the power of negative x. Since I want to move those exponents around, I'm going to multiply each side by the logarithm so that we can use our logarithm principles to continue to solve. Now that I've multiplied each side by the logarithm, I'm able to use my exponent rule and bring in front x plus 3 and negative x into the front. What I'm then going to do is distribute the logarithm to remove my parentheses. So I'll have x log 4 plus 3 log 4 minus x log 3. Notice that on the left I have an x value and on the right I have an x value. I want to get them together. So I'm going to add x log 3 and subtract 3 log 4. So interchanging these two by subtracting 3 log 4 and then adding x log 3. X log 4 plus x log 3 are not the same, so we cannot combine them together. But what I can do is factor them. Since they both have an x value, I can factor out that common factor of x, leaving me with the inside log 4 plus log of 3, which is simply just a number. I then can divide both sides by log 4 plus log 3. And when I use a calculator, I'll end up with approximately 1.6737. Again, using the intersect method. On one side, I'll have 4 to the power of x plus 3, and on the right side, I'll have another line for 3 to the power of negative x. Where they intersect here gives us our solution. So a great way, again, to double check that what we're finding algebraically certainly is what we're finding graphically. Now we've got e to the power of x plus e to the power of negative x minus 6 is 0. I'm going to rewrite e to the power of negative x using a positive exponent. We know that a positive exponent will rewrite this as 1 over e to now the positive x. And then I'm going to remove the fraction. Our common denominator is e to the power of x. So I'm going to multiply everything by e to the power of x so that I can remove not only that negative exponent, which we turn to a fraction, but then all of the fractions. And what we do to the left side, we have to do to the right side, but we know that 0 times 0 will be 0 anyways. All right, so here I have e to the x times e to the x. When I have a power to a power, we add our powers together. So I'll have e to the power of 2x. So multiply our bases, we add our exponents. Then I'll have e to the x times here, which our e to the x will end up canceling, so I'll have plus 1. And then I'll have e to the x times negative 6, which is negative 6e to the x, still equal to 0. I'm going to rewrite these in descending order by exponent, so e to the 2x minus 6e to the x plus 1 is 0. We're going to write this as a quadratic so that we can factor. So we're going to write as a quadratic. I'm going to let u equal e to the x. Therefore, u squared, if I were to square both sides, is equal to e to the 2x. So I'm going to replace e to the 2x with u squared. And I'm going to replace e to the x with u. And now that it's in quadratic form, there's nothing that multiplies to 1 and adds to -6. So I have to use my quadratic formula. A is equal to 1. B is equal to -6, and C is 1. X equals opposite B, I should say u, not x, because we're solving for u. Opposite B, so the opposite of -6 is +6, plus or minus the square root of b squared minus 4 times A times C, all over 2 times A. Simplify underneath our radical. We'll have 36 minus 4 over 2. 6 plus or minus the square root of 32 over 2. 32 we can rewrite using 16 times 2, and the square root of 16 is 4. So 6 plus or minus 4 square root 2 over 2. I see that my coefficients here are all divisible by 2. So 3 plus or minus 2 square root 2. But we're solving for e to the x, not u. So I need to replace my u back with e to the x. We know we can get rid of the e value by multiplying both sides by the natural log. The natural log will end up canceling, so I'll have x is equal to the natural log of 3 plus 2 square root 2 and the natural log of 3 minus 2 square root 2, which gives me approximately 1.76 and approximately -1.76. This time when I graphed, I used the zero method. I used the zero method here because our graph or our equation was already set equal to 0. So on the left-hand side, I said just simply put y is equal to e to the x plus e to the -x minus 6, and I found our two values. The values where they cross 0, since it's set equal to 0, where is our graph equal to 0, which is what it's saying here, as -1.76 and +1.76, which we found algebraically. When we try to solve a logarithmic equation algebraically, we're trying to obtain a single logarithmic equation first. So when I look at log base 3 of x is equal to -2, we know that we can rewrite this using our base of 3 to the power of -2 is equal to x. We can rewrite this using a positive exponent, so 1 over 3 squared, or 1/9. Still using the intersect method, I have y is equal to log base 3 of x, and then y is equal to 2. They intersect certainly at 1/9, or 0.1 repeated. Here we have log of x plus log of x plus 3 equals 1. We're going to use our multiplication rule. Since we're adding the same bases, we can use the multiplication rule to combine these together. We know that if I don't see a base, it's automatically 10. The multiplication says that if we are adding our logarithms together, we can multiply their of pieces. So x times x plus 3 is equal to 1. I then can rewrite this using exponents. So 10 to the power of 1. So 10 to the power of 1 equals x times x plus 3, or vice versa, just flipping it over. 10 to the power of 1 is still 10. I can distribute, so I have x squared plus 3x. Then subtract 10, and now all of a sudden I have a quadratic. I can find two values that multiply to negative 10, but yet add to 3. 5 and negative 2 work, giving me x minus 2 and x plus 5. Setting them both equal to 0, I'll have x is equal to 2 or x is equal to negative 5. We know sometimes that they don't work, and when I'm using the intersect rule, I had y equal to the left side, and then I had y equals 1 on the right side. I see that they're only crossing one time. So one of these solutions may not work, which is why it's important that we check our solutions. So when I check, we'll start with 2. When I replace my x values with 2 and use my calculator to help me, I'll have log of 2 plus log of 5. Using our product rule, that becomes log of 2 times 5. And we know that anytime we have the base to here and here is equal to 1, using one of our rules, so it certainly is a true statement. Or utilizing your calculator, substituting in log of 10 of 10 would also produce the result of 1 if you forgot the rule. And when I check number 5 here for negative 5, I'll have log of negative 5 plus log of negative 5 plus 1. Oh dear, negative 5 we know is not a solution because it is not, a negative value are not defined. It's not in the domain of logarithmic functions, so it cannot work, which is why we only see one value as a solution. A few more examples to kind of drive this home for us. Here we have log base 3 of 2x minus 1 minus log base 3 of x minus 4 equals 2. We're going to use the subtraction rule or the quotient rule, that when we're subtracting, we're able to rewrite this using division of log base 3 of 2x minus 1 over x minus 4. We can rewrite this by taking 3 to the power of 2, writing it as exponents, is equal to 2x minus 4. I know that 2x minus, 3 squared is 9. To get rid of these items, I'm going to multiply both sides, get rid of my fraction here. So I'm going to multiply both sides by x minus 4 such that the x minus 4 binomials cancel. I can also distribute. So now I have 2x minus 1 is equal to 9x minus 36, much nicer way to solve. I can combine like terms, so I'll start by adding 1 to both sides. So 35 is equal to 7x, and adding 2x, subtract 2x and add 1. Oops, not add 1. I'm so sorry. Add 36. So subtract 2x, add 36. We have 35 is 7x, divide by 7, x is 5. We want to check to make sure that that works. So I substitute 5 in wherever we see x. We'll now have log of 3 is 9 minus log of 3 of 1. I know that 3 to what power is 9, and then 3 to what power is 1. Well, that gives me 2 minus, since 3 squared is 9, so 2, and 3 to the power of 0 would give me 1. Therefore, 2 minus 0 is 2, and it checks out. We can also use the intersect method, which we see that it does work out as well. Let's try one with the natural logs, and we're subtracting with the natural log here. So we can use the quotient rule. We can combine them together by the natural log of 4x plus 6 over x plus 5. Using the equality rule, I know that I can drop in both sides by the natural log since it's already written in the natural log. So the natural log can be dropped, and I'm just left with 4x plus 6 over x plus 5 is x. Let's get rid of the denominator by multiplying both sides by x plus 5. Oops. So our x plus 5s cancel on the left. And when we distribute the x plus 5s, we'll have x squared plus 5x. We can get both sides into quadratic form. So what multiplies to -6 but yet adds to 1? Looks like -2 and 3 will work. So x plus 3, x minus 2. When I set both sides equal to 0, we'll have -3 and 2. We know that we can't use -3 because -3 is not in the domain. But certainly that 2 does check out. And then we see using the intersect method that 2 also works as well. Sometimes we're going to come across problems that simply can't be solved algebraically very easily. So using a graphing calculator can certainly help us. In this example, I'm going to show us how to use the intersect method and the zero method with a value that's a little more difficult to solve algebraically. So we have to rely on some of our graphing skills to do that. So if I were to set both of my sides of the equation and set the left side equal to y and the right side equal to y, we see that they cross in 2 locations. We know that we're going to use the first coordinate, the x value, to find the solution since we're solving for x and x is the first coordinate. That are approximately -6.471 and 6.61. Another way to solve this exact same problem is to use the zero method. Where does it cross the x-axis? But before we can do that, we'll have to subtract and set this equal to 0. So we'll have to subtract 2.08x and subtract 6.2 and bring them to the left side to set this equal to 0. So first we have set it equal to 0, and all we need to do is graph the big long function itself and then determine where it's crossing the y-axis, where it's crossing the x-axis. So again, there's 2 places with which it's crossing the x-axis, and these are the 2 solutions or the 2 zeros. We see that they're approximately -6.471 and approximately 6.61. The exact same solutions that we found using the intersect method, but this time we're using